Okie dokie. So here we are in the mitochondria, and I'm going to show you the last part, or the most important part of cellular respiration, which is a process called oxidative phosphorylation. So it's oxidative because we're going to do redox reactions where NADH and FADH are going to drop off their hydrogens to this electron transport chain. And then through that process of all the redox reactions in the electron transport chain, we're going to phosphorylate ADP to make ATP. So here's how it works. So in the mitochondria, if you remember, there's an inner membrane and an outer membrane, and there's this space in between them called the intermembrane space. That is where we're going to build up a proton gradient. So if you remember for one of the first slides I showed you in today's lesson, the proton gradient is responsible for spinning this thing called ATP synthase, which will then cause ADP plus P to form ATP. So if we can get this thing spinning, we can make ATP. Well, in order to create the proton gradient, we have to be able to pump protons on this side of the membrane. Okay, so let me show you all the players. It's kind of crowded in here. We got ADP, which we're going to use to make ATP. So I've got 4 molecules of that, but I'm going to take these out of the picture for right now. We have the phosphates that we're going to use to phosphorylate ADP. These are the little letters, the T's, and I'm going to change the D's into. This is oxaloacetate, but we don't need that right now. That's part of the citric acid cycle. These are oxygen gas. That's going to be our electron acceptor molecule. So these are going to be reduced when the electrons come down this chain. And then we have our hydrogen carriers. I've got 6 NADH here because I got 3 hydrogen on this NAD, 3 hydrogen on this NAD, so that's 6 NADH. And I've got 2 FADH here. Okay. So embedded in this inner membrane of the mitochondria are electron carriers. These are proteins embedded in the membrane, and in each electron carrier there's a metal atom that will pull the electrons from NADH. Each consecutive metal atom is slightly more electronegative than the one before. So when this one receives an electron, this one will steal it. And then when this one receives an electron, this one will steal it. So that we get this like hot potato chain of electron carriers. When the electrons are moving down this chain, it powers a proton pump to pump protons from this side of the membrane to this side of the membrane so that they accumulate on this side of the membrane. So here's how this works. So NAD donates its proton and its electron to the first electron carrier. But then the second electron carrier steals the electron from that one. And then this proton will then be pumped into the intermembrane space. Then this electron will move to the next electron carrier because it's more electronegative. And then the most electronegative thing of all is oxygen, and it will pick up the electrons at the end of the chain. Now we're going to see how this is going to turn into water, but not quite yet, because right now it only has 1 electron. So we keep doing that. The next NADH comes, it gets oxidized, this gets reduced. The electron carrier takes this electron, this proton gets pumped, the electron goes down the chain, ends up on oxygen. Okay, so we're going to make water. So I know I have 2 oxygens and water only has 1, but you're really only going to have 1 oxygen per water. So I'm going to pull this apart. We'll get the water made from both of these in just a second. Okay, so far I've got 1 oxygen and 2 electrons. So now what's going to happen is we've got a proton gradient. And these protons, they can't go through the membrane anywhere. And they're like really wanting to go through the membrane because there's a gradient. So there's a concentration gradient in that there's a lot more H plus on this side than on the other side. There's a pH gradient in that the pH is lower on this side than this side because there's more hydrogen ions. And there's a charge gradient in that there's more positive charges on this side than this side. So these protons are like, get me through, get me through. They could only go through a pore right next to this little motor. And so that's where they go through. And as they go through, just like water going through a turbine in a dam, as they go through, they spin this. And so there's a continual flow of protons through the only place they can go through. This spinning is going to activate an enzyme at the base of this. So this is ATP synthase. And it, as the word implies, it makes ATP. So the two substrates for ATP synthase are ADP and P. And when this spins, it causes this phosphate group to just bind to the last part of ADP to make ATP. And then that's our product, ATP. Meanwhile, these two protons can then join their electrons on the oxygen to form water. So so this is two hydrogens then again, and this is the oxygen. So the fate of oxygen gas that you breathe is it becomes water in this last step of the electron transport chain. And the purpose of the oxygen is to grab the electrons, to keep the electrons flowing. As long as we have electrons flowing, we have the protons flowing. And as long as we have the protons flowing, we have ATP synthase moving, and we can continue to make ATP. Notice that there's a lot of ATP synthase molecules on this inner membrane. The inner membrane's folded so you get a lot more of these complexes in a smaller space. So it's not that this is like this happens, this happens, this happens, and then this happens. This is always happening as long, all of these are moving, as long as there's a proton gradient and the protons are flowing. So if you don't have oxygen, so let's say your heart stops moving and you stop pumping oxygen to your cells, and the oxygen all goes away. There's nothing to pick up the electrons. So when the electrons go to here, there's no place for them to leave. And so when the next NAD donates its electrons, those electrons are going to go here and get stopped. And then same with this one, they'll go to here and get stopped. And now this NAD has no place, NADH has no place to donate its electrons. So it gets blocked up like a traffic jam. And so no more electron flow. So once the electron flow stops, you'll stop making the proton gradient. This will dissipate, and then we'll end up with no more proton gradient, no more ATP. So then if you don't have oxygen, the only ATP you can make is the ATP you made in glycolysis. And as you'll see in the next video, glycolysis will run into fermentation, and that only gives you 2 ATP per glucose, which really isn't very much at all. So if you oxidize all your NADH, and so each NADH that gets oxidized produces 3 ATP, and every FADH that gets oxidized produces 2 ATP. So the reason for that is that when FADH donates its electrons, it donates them to the second electron carrier of the chain. So it donates them here, instead of up here. So you pump fewer protons if you start here, and so you get less of a proton gradient with FADH. But otherwise, it's the same idea. Oxygen still picks up the electrons at the end. You still make water. You still make a proton gradient. So FADH is just slightly less efficient as NADH is. That's pretty much it. So you make altogether, since you have 10 NADH altogether in cellular respiration, you make 30 ATP from the NADH. And since you have 2 FADH, 2 times 2 is 4, so you get 34 ATP altogether. So you get 34 ATP in oxidative phosphorylation only 2 ATP in the citric acid cycle and 2 ATP in the in glycolysis. So the vast majority of the ATP is made in oxidative phosphorylation. The other word I wanted to show you is, the other vocabulary word is called chemioosmosis. And that's really just the term they used to talk about the proton gradient. So instead of water being the thing that moves in osmosis, they're talking about this chemical osmosis of moving the protons through the membrane. So chemiosmosis is referring to the proton gradient. The electron transport chain is referring to the electrons being moved down from one electron carrier to the next. Oxidative phosphorylation is this whole process where we're using redox reactions to phosphorylate ATP. Okay, that's it. Okay.